Welcome to Lesson 5, example number 2. And it is asking us to determine the safe moment M that may be applied to the beam of example 1 if half of the total applied moment is dead load and half is live load. So we're wanting to find safe moment M. So we're find M. Half of it is total applied moment is dead load and half is live load. Alright. And this isn't 100% intuitive what they're asking here, and I think it's a very difficult question to say. What? What do you mean? What is the applied M? Because this isn't the most realistic example ever, but that's all right. We're going to see if we can solve it despite. So we know mu equals 1.4 dead load. Oh, sorry. Let's do this. Dead load plus 1.7 moment of live load, not dead load again. Live load. And this is going to be what we call a load combination. And it mentions in the study guide that we're using strength design. So we're not doing allowable stress design because that, remember, when we did allowable stress design for steel and wood, we would say, well, let's say for steel, you would say the bending stress equals 0.66 of the yield stress. So you take, this is your yield stress, which would be, in this we've been doing 36 KSI. Then you multiply it 0.66, or you could say, not you could say, but the shear stress was usually 0.4 of Fy. But you wouldn't load, you wouldn't change what the what your load is. You don't factor your load, you just use your, well, you would call unfactored loads, or sometimes people call them service loads. But this time, this is the first time we're actually factoring our loads. So this is your moment from dead load, that's your moment from live load, and we're multiplying it by 1.4 and then 1.7. So from here, this is the confusing part. You're saying that half is MDL and half is MLL. So you could substitute in 0.5 M for that, and then 1.7 0.5 M. And that is kind of confusing, because why, in what realistic scenario would you say, well, we're going to have half of the unfactored load be dead load and half of it be live load? That's not typically how you do it. You'll figure out what your loads are, and then you go that way and you get your MU, but then you have to figure out and design your beam phi mn bigger than MU. And I'll write that up here. Phi mn is your capacity, needs to be greater than or equal to MU, which is your load. And this is your capacity, or your resistance, as some people like to call it. Alright, so it's saying that essentially this is the beam that we're using, and if this is the beam, and if we were maxing out the beam, I think we had 132.7. Look at my calculator. No, that's not right. Let's go back. My calculator says 205.7. 205.74 or 2.5.7. 205.7 is our capacity. So we're going back and we're saying that, okay, so if we're maxing out that, what is our maximum applied load if half of it is applied for each? If it's half unfactored, half of it's going for dead load and half of it's going live load, then we factor it, and all that will equal this, or under. But of course we're maxing out, so we want to say it equals that. So let's go ahead and solve for this. let's just go ahead and solve this and simplify a little bit more. So 1.4 times 0.5 equals 0.7. So mu equals 0.7m plus 1.7 times 0.5 is 0.85. So you end up having 0.85 plus 0.7 equals 1.55 m. Remember, we want to max it out, so we want to make it equal to, we want to say, okay, we want to make mu equal Vmn. Since we're maxing out our capacity, we want our load to equal our max capacity, so we need to put it in there. So you get 1.55 m equals 205.7 foot-kips. And then we want to go ahead and solve for m. So you want to divide 205.7 divided by 1.55, obviously showing your algebra so I don't confuse anybody. I'll put it over here. So 205.7 divided by 1.55 equals 205.7. I messed up my calculator. 132.7. And that's in foot-kips. Alright, let's check that and see if it's right. 132.74 foot-kips. We have 132.7 foot-kips. And I hope that makes sense. Going back, I think it's more intuitive going the opposite way. Once you get this, does it make sense? So you say, okay, what you're saying is that I have my MDL equals 132.7 foot-kips. My MLL equals 132.7 foot-kips. And actually, I forgot to say, it was, you could say MDL equals 0.5 m, and same thing for ML. So we have to actually 0.5, hit that by half, since it's half. Remember, MDL equals that MLL. Moment of live load moment equals 0.5 m, so I forgot to do that. So we get 132.7 divided by 2 equals 66.4, let's say. And remember, I'm rounding, so it's not going to be coming out perfect. I might be slightly over, but 66.4. So when we go ahead and put it in, you say MU equals 1.4 load factor, MDL, which is right up there, plus 1.7 m live load equals 1.4, 66.4 foot-kips. I'll go ahead and put it in there, plus 1.7, 66.4 foot-kips. And this should be around, should be, hopefully it should be exactly, but remember, we've been rounding, so it's not going to be exact. 1.4 times 66.4 plus 1.7 times 66.4, 205.8 foot-kips. And that's right on, for all intents and purposes. We rounded, so it's supposed to be that exactly, but we're close enough. So that is your ultimate, what I like to call ultimate moment. Some people might call it, it's your factored moment. And sometimes you want to go in and you'll see later on you want to get stuff, and I don't know if you actually go through this in this concrete section, but you might want to also calculate your service moment, or some people just call it M. You might want to call it MS. I'll call it MS for this purpose. So this is your service moment. This is, and the reason you want to do that is you have service loads like deflection. You don't want to combine. This is for strength. These load strength designs, these load combinations, they're for strength. So you don't want to put it right up to 100% strength. But deflection, you go in there and you say, well, you know what, this is what we're actually going to have. We don't have to design for overloads, because it's not going to fail. It's just going to bend a little bit more than we wanted it to. So you go in and say, well, our strength, or I mean our service moment is what, 66.4 foot-kips plus 66.4 foot kips. And we know that's 132.7 foot kips. And you can see the difference between factored and unfactored. This is factored, and this is unfactored. This is service, or unfactored. All right, and that's just to help you out. You didn't need to go back through, but hopefully that gets you to better understand what these load factors are doing. And then you could actually, I would call, when you're doing, I kind of explained what a load factor is. And those are load factors right here, and they are put in with load combinations. And I'll do videos on this in the future, obviously, what different load combinations are, and there's a ton of them. But this is a pretty common one. It's usually like a strength 1 or strength 2, I forget. My ASCE 7 book's in the other room, so that might be in there. You might want to look in there if you have one of those books, and it will tell you different load combinations you can use. And since you're doing concrete design, I would go to the ACI book. And anyways, I hope that gives you, actually I was going to go through this, but those are load factors right here and right here. Load factors, and then we have resistance factor is that phi mn. So you're actually saying 0.9 is your phi factor for this. And that's the more of a resistance factor, and I think it's like 0.85 for shear and whatnot, but you can find those in your code books. All right, I will see you in the next video.